All right, so we're going to begin now. Hello, everyone. Welcome to the 34th online Spintronics seminar. Thank you for joining us. This is Xinfan from University of Denver. It's my great pleasure to introduce our speaker today. Dr. Zhang Avci obtained his PhD degree in material science from ETH Zurich in 2015 under supervision of Professor Pietro Gambardella. His thesis focused on current-induced effects in ferromagnetic heterostructures with strong spin-up coupling. He then moved to MIT as a postdoc and worked on magnetic insulators for spintronics applications in the group led by Professor Jeff Beach. He returned to ETH Zurich in summer 2018, where he's currently working as a senior postdoc. His latest research is on the spin charge interconversion and magnetic coupling phenomena in multi-layered ultra-thin films. So without further ado, Zhang, please go ahead with your talk.
Thank you very much, Shin, for the kind introduction, and thank you and Kirill for organizing this seminar series, which is a wonderful platform to connect with our peers and share our research. So today in this seminar, I will be talking about magnetic insulators with perpendicular anisotropy. So here is my outline. So first I will shortly answer the question of what attracts me in magnetic insulators. And I will try to convince you that this material family has an immense potential for spintronics research and future applications. In the second part, I will present recent advances in spin torque control of magnetization in magnetic insulators with perpendicular anisotropy. Then I will discuss the emergent chiral magnetism and our results of current-driven fast and efficient domain wall motion in these materials. And finally, in the last part, I will give an overview of our latest report of a magnetotransport phenomenon, which allows non-local detection of magnetization vector in magnetic insulators based on a thermal spin drag mechanism. All right, why magnetic insulators? So magnetic insulator is a very large family. So I will mostly speak about magnetic garnets. So magnetic garnets have been known and studied for more than 60 years. So these are the first papers that I could find that where they report the discovery of yttrium iron garnet and rare earth iron garnet. So it's really like more than 60 years. And their properties in the bulk form are very well understood and very well known, thanks to the extensive research done in the 1960s through 1980s. So after 1980s, there was the discovery of the GMR and RKKY and perpendicular anisotropy. So the focus has shifted in metallic layers. But before then, the popular material systems were actually magnetic insulators. So I'm especially interested in rare earth iron garnets. So let me briefly explain, maybe give a very short tutorial on how the magnetic rare earth magnetic garnets are, they look like in their very simple unit cell. So actually the unit cell of these garnets are very complex. They contain 160 ions in the unit cell, which consists of about this much number of rare earths, iron and oxygen. Then magnetically, basically, so we can understand the magnetization behavior by looking at this very simplified unit cell, where you have tetrahedral sites occupied by iron, trivalent ions. Then you have this octahedral site, again, and iron. And then you have this dodecahedral site that is occupied by the rare earth, or that could be also non-magnetic other ions as well. So the magnetism occurs due to the fact that you have an super-exchange interaction between this tetrahedral and octahedral site through this connecting oxygen ion that is here. And this is the strongest interaction in this material. So you have basically like anti-ferromagnetic coupling, but since you can here you see that there are actually more tetrahedral sites than octahedral sites in the material. Therefore, it gives rise to a finite magnetism. So that's a ferrimagnet. On top of that, you have this rare earth that contributes to the magnetization, but it basically the main coupling of this rare earth is to this tetrahedral site, and that couples also is antiferromagnetically due to this super exchange, but the interaction between this side and this side is very weak, so it's negligible. Therefore, so for instance, due to the different magnetic contribution of this side, you see here on the right side that the saturation magnetization it behaves very differently as a function of temperature when you have different rare earths here. So also the magnetization of this rare earth vanishes at a relatively low temperature, like, okay, still high, but relatively low temperature. The Curie temperature, where the total, like the magnetic order vanishes, actually it is more or less the same, independent of whatever rare earths or other ions you have in there. And this Curie temperature remains pretty high for room temperature applications. Therefore, it's good for us. It's good for doing some spintronics research and look for some applications. Okay. So let me look at the advantages of these rare earth iron garnets or magnetic insulators in general for spintronics. So there are two kinds of properties we can talk about. One is this tunable magnetic properties. So one of them is this saturation magnetization, because as you have seen that depending on whatever like like this rare earth that you use, you can get different saturation magnetization. But also the strain state gives rise to different anisotropy scenarios. So you have also tunable magnetic anisotropy. You have also a tunable damping. So depending on the of course on the composition, and you can also get magnetic compensation temperature where the material acts like an antiferromagnet. You also have an angular momentum compensation, which is very useful for ultra-fast dynamics that I will briefly explain later. And also I have to tell you that because of this, you know, like the complexity of the material is actually could be seen as a disadvantage, but if you understand it well, it could be, it's actually an advantage to be able to tune precisely all these parameters via, for instance, rare earth choice, substitution, substrate choice, or varying temperature, or materials that you can grow on top that will change also the properties of these materials. On top of that, we have some general properties that are very appealing. For instance, all these materials, they have very high structural quality. They grow epitaxially in single crystal forms. They have very structural robustness against external factors, like because they are oxides, basically they are naturally protected at environment. So they also give very high flexibility of growing any type of material on top, just to do some science without compromising their properties. And then we now know also that, okay, all these studies have been done in bulk materials or micrometer materials that were grown by liquid phase epitaxy. But right now we know that we can grow these materials by pulse laser deposition or even sputtering. So all these things basically gives us some advantages for spintronics. For instance, it gives us possibility of lithographical patterning because they are ultra thin, so in the order of a few nanometers or maybe 5, 10 nanometer. You can also obtain and tune the perpendicular magnetic anisotropy, which is very suitable for spintronics. You can get efficient spin current generation by coherent magnons or incoherent magnonic excitations like a spin-Seebeck effect or like a spin pumping. You can get a possibility to explore a wide range of materials for spin current source or spin current detector, like metals, alloys, and TM, like transition metal die, chalcogenides, or topological insulators, which you can combine with these magnetic insulators. And this high structural quality gives low pinning, so it's very efficient domain wall and skyrmion motion you can obtain. And you get also very low switching current because you can tune them magnetization, even though the materials can be relatively thick with respect to their metallic counterparts. You can still use very small current for switching these materials by using, for instance, spin orbit torques. And as I mentioned earlier, that this ultra-fast dynamics can be obtained if you get, so if you engineer your material to have get the angular momentum compensation at room temperature, for instance, and also for damping, you can obtain very low damping. Actually, one of like the lowest record low damping of material is yttrium iron garnet. And this material has been, well, you can use this material for very long range signal transmission via magnetic excitations. So all these advantages are very motivating for me. So I hope that I'm able to also motivate you. And so let me briefly explain more recent research. So a few years ago, so when I joined the group of Jeff Peach at MIT, so my colleagues at MIT, they have grown the first thulium iron garnet film with perpendicular magnetic anisotropy down to 5 nanometer thickness, maintaining bulk-like properties. So here I show you a set of structural and magnetic characterization. I'm not going to go through all the details, but as you can appreciate here is that you have the thulium iron garnet grown on top of GGG substrate, and you see it's a perfectly like epitaxial growth, a single crystal structure that is also appreciated here in the XRD graph. So you see here thulium iron garnet is slightly strained, so that strain gives rise to a magnetic anisotropy to be out of the plane, so which is very good for us. And this can be confirmed by either in a global VSM measurements by just looking at the microscopic sample, or in a more like local measurements of magneto-optical curve effect. These magnetic loops are taken with an out-of-plane field sweep. And on top of that, this magnetic force microscopy image is basically shown the demagnetized state of this thulium iron garnet, and showing you this typical labyrinth domain structure in this material. Okay, and thulium iron garnet was the first material, but of course this is one of the many materials that you can grow perpendicular. So terbium iron garnet, europium iron garnet, dysprosium iron garnet, and also I forgot to add it here, but also gadolinium iron garnet. All these materials have been later on synthesized, and it became more or less like a standard, the growth became something standard of these materials. Okay. So in the next part, I would like to talk about how we can control the magnetization in these insulators by using electrical current. So spin torque control. But maybe before explaining that, let me take a step back. So before being able to control this magnetization, I want to explain you how we can actually detect magnetization by using electrical current in these materials. So luckily we have this effect that has been discovered about 7 years ago. This is spin Hall magnetoresistance. So spin Hall magnetoresistance, let me briefly explain. So here in the pink, you have this magnetic insulator. And if you have a metal with a large spin orbit coupling, for instance, platinum next to it, this platinum will generate a spin Hall effect. Spin Hall effect means that when you send a charge current through this material, it will deflect. It will, due to the spin dependent scattering, you will have a spin current transverse to the charge current that is running. And that spin current will interact with the magnetization of this magnetic insulator. Even though there's no current going into the magnetic insulator, the resistance of this platinum will depend on the magnetization direction of this of the insulator. Therefore, in the longitudinal measurement scheme, like when you measure a longitudinal resistance, that the resistance will depend on the Y component of the magnetization, taking into account this coordinate axis. But also there is a transverse component of this spin Hall magnetoresistance that gives rise to two kinds of signals. One is proportional to the dot product of X and Y, MX and Y. And this is basically the dominant contribution. And then you have also a secondary contribution that is proportional to the perpendicular component of the magnetization. And you can also make, if you know a little bit of this anomalous Hall effect and planar Hall effect in metallic films, this is basically equivalent to metallic films, just that we measure it in platinum without sending current through the magnetic material, and also the amplitude of the effect is much lower than in the metallic cases. But it's not, let's say, it's not so, let's say it's low, but it's not as, it's still very easily detectable, let's say. So here I show you an example. So you have the toluene iron garnet and platinum on top. And here I show you two different measurements. So now toluene iron garnet has perpendicular anisotropy. And you see here is that depending on which angle you apply the field, you get an enhancement of the signal that saturates above certain field value. The saturation is due to the fact that magnetization fully saturates in plane, where you get the saturation here. And if you look at these angles, you will see that actually this corresponds, 45 correspond to maximum MXMY, 135 is the minimum MXMY, and 0 degree is basically no signal. And this is interesting. Well, this is interesting in itself, but what's more interesting for me is to be able to detect the perpendicular component of the magnetization, and that's easily done by using the anomalous, this out-of-plane field sweep. And you see here that although it's small, it's very clean measurement of the out-of-plane magnetization. So, so the message from this slide is that magnetization vector can be detected by simple Hall effect measurements, and spin current injection into magnetic insulators is efficient because these kind of signals would not occur if you didn't have this kind of mechanism where the spin current interacts with the magnetization. But this is a qualitative like judgment, let's say, on the efficiency of the spin current. So we know that now we can inject spin currents. So let's see if we are able to switch the magnetization. So here is the I explain how we achieve the magnetization switching. So here you see the typical Hall effect, like anomalous Hall effect signal, signal that is during an outer plane field sweep. And now we are injecting, well, we are sending a current, and we are applying an in-plane field, and that in-plane field gives rise to like breaking of the symmetry, because you have the spin Hall effect will generate a spin current that is in plane and perpendicular to the current, and magnetization is out of plane. Therefore, it will rotate around this the direction of the spin current. However, if you apply now an in-plane field, you can break this rotational symmetry, therefore switch the magnetization from one state to the other depending on the current direction or the field direction that you apply in plane. But the field itself does not switch the magnetization, but together with the current, you are able to switch. So you can go you can also look at the threshold current for a given field value, and you can also study this kind of threshold current behavior as a function of the in-plane field. And we basically are able to get all the physics that we know from the metallic systems, and that the more field you apply, the threshold current goes down. And this is basically a confirmation that we are switching the magnetization by spin orbit torques and not by other thermally induced phenomena. So these measurements were done with millisecond pulses. So we are also able to switch the magnetization with nanosecond pulses. So although, okay, these signals, they don't look as clean, but here is the switching percentage. This device, I'm not showing you the device here, but it's a device, it's a whole cross that is of the order of a few micrometer. And we are, even though it's a relatively large device, we are able to switch the magnetization on the order of a few nanoseconds. So this brings me to my messages from this slide, is that there are large spin orbit torques, efficient switching comparable to all metallic ferromagnet normal metal bilayers, because these current densities are comparable to, for instance, platinum cobalt, but here the toluene iron garnet is 8 nanometer thick versus in platinum cobalt usually is a nanometer or below. So, and also this kind of fast, let's say, switching, it is indicative of a fast domain wall motion, because we know that in micrometer scale devices, switching, it's mediated by nucleation and domain wall propagation. And this gives me a clue, or it's a signature, that the domain wall motion in these materials could be very fast, because if you just make a very envelope calculations using a few micrometer of distance with a few nanoseconds of switching times, then you are almost in the order of a kilometer per second. But that needs to be proven. So that brings me to my next slide. So here in this part, I'm going to talk about a new emergent chiral magnetism that we discovered in this very same materials, like in rare earth iron garnets. And I'm going to discuss some exciting current-driven domain wall motion results. And let me briefly explain my device. So here I'm using a, well, this kind of device where I can nucleate a domain by using a nucleation line here. And I'm not able to use a wide field mode, so I can only measure the magnetization by using a local focused laser and using a magneto-optical Kerr effect. So, but this basically I can use it in a scanning mode, so I can measure in different places in the device. But we need to be careful when doing this kind of measurements because the domain wall could come from different places in the device. So the control measurements are extremely important if we are not able to visualize the domains in this device. So here I'm explaining the effect of nucleation and the effect of nucleation and the effect of current injection. But let me go like slowly because it looks a bit messy because of the overlapping different data sets here. So the solid black line, it's a current. So it's in the absence of any nucleation and in the absence of any drive current that I sent through the track. So that gives me like a standard hysteresis with a coercivity of the order of 35%. Then in the next measurement, what I do is that I start from a negative field, I ramp up my field, and on the way back at around 0, I nucleate a domain here. And then I see that immediately the coercivity drops to tenors, that which means because we already nucleated the domain by sending this nucleation pulse here. This means that we are able to actually nucleate, and that the switching of the track, or let's say if we are probing here, the domain wall sweeps through underneath the laser spot at a much lower, much reduced field. But the interesting observation that I had was that when I send now a DC current, while doing that, I saw that depending on the current direction, the coercivity or the reversal event changed, like shifted as a function of the out of in out of plane field, which means that there might be some effect of the current on the domain wall. So I wanted to quantify that. So this is the quantification for two types of domain walls. So I created first an up-down domain wall, and I checked what happens if I inject this kind of like these current densities through the track. And I saw that the propagation field, which I write here as a HP, the delta of the propagation field, basically. So the delta is the difference between the dotted line here and the red line or the blue line. So this is my delta. The delta propagation, so the propagation field difference linearly scales with the injected current. And when I reverse the domain wall polarity, so now I'm measuring down up, then that effect reversed as well, which means that that's clear effect of the current on the domain wall. Let me briefly explain you that if the domain walls were of block type, as shown here, the effective field of this spin current from the spin orbit torque would be actually 0. Which means that if the domain walls were block type, then I shouldn't see this kind of behavior. Whereas if the domain walls were Néel type, then I should be able to see this kind of behavior. But I don't know if the domain walls, okay, I know that there's some Néel character, and I know that it's chiral because changing the domain wall from up down to down up, the sign of this effect changes. But I just need a quantification. So now I have so just by taking this slope, I have a clear quantification. So that is 15 Ersat per 10 to the 11. Okay, this is the quantification that I have based on the domain wall measurements. I know that now I can quantify the damping like torque by using a harmonic Hall effect technique. So okay, I'm not explaining the harmonic Hall effect technique, but maybe some of you know. It's a standard method to quantify spin orbit torques in metallic, metallic ferromagnetic heterostructures, and it became also kind of useful for even in insulator systems, because the signals that we observe basically is very similar to like in the metallic case. So you have anomalous Hall effect like signal, you have planar Hall effect like signal. So okay, anyway, so the idea is that here I do this quantification, and what I find is that the damping like torque I find from the harmonic quantification is exactly the same as the damping like I find from this one, which means that actually the effect of the damping like torque on the domain wall is maximum. That and it must be that the domain wall is fully Néel type, okay, and not something in between block and Néel. To further confirm that, what I did is that now I'm looking at, so I did a kind of similar but also different experiment, let's say, that I generated a domain wall here and I looked at the critical current to start moving this domain wall. So there's no out-of-plane field involved in this one. I'm just moving the domain wall purely by current. But while doing that, I also applied an in-plane field. So in plane field, what it's going to do is this basically. So if you have an Néel type of domain wall at remanence, at zero field, so if you apply a field along, anti-parallel to the magnetic, so the spin orientation of the domain wall, then you can rotate this domain wall into a block type. And if you apply a field even stronger, then you can change the chirality of the domain wall by just using this. So here in this data shows me exactly this here basically. So for instance, for a down-up domain wall, which is the figure here, that at zero you have negative current you need. If you apply a positive field, the current that you need doesn't change. But then if you apply a negative field, basically it spikes. So there's like a very strong increase of the critical current. But at some field, that the critical current changes sign. So to move the domain wall in the same direction, I need an opposite polarity of current. So which indicates that the chirality of the domain wall changed. So I can also fit these data and I can quantify not only the DMI, but also the domain wall and isotropy, but it gives me like very reasonable values. DMI is indeed small with respect to platinum cobalt, but it's still enough to make the domain wall fully Néel type. That is what's important indeed. And but what was puzzling for us is that in this kind of system, we have basically that the platinum and toluene, so platinum is on top of toluene iron garnet. And so we observe a left-handed chirality. But left-handed chirality for platinum cobalt systems, for instance, it occurs when platinum is underneath the magnetic layer, not on top, which means that here we would expect a right-handed chirality. However, we got a left-handed chirality. Why is that? So we wanted to observe is actually platinum is the well, it gives rise to this or something else. So we did measurements on toluene iron garnet platinum, left-handed chirality, terbium iron garnet platinum, left-handed chirality. Then we inserted copper in between. Again, the domain walls are left-handed chirality, which means that actually platinum is does not need to be in contact with terbium iron garnet. So platinum does not play a significant role here. So what we concluded, along with other work here that I refer to, we concluded that the DMI must come from the GGG interface. On top of that, my colleagues at MIT, they have also made they also studied afterwards more in detail, and they found out that actually the rare earth elements is crucial to have the DMI in the system. So if you measure yttrium iron garnet with perpendicular anisotropy, then the DMI effect, the DMI vanishes. There is no chiral magnetism occurring in that material. So GGG and iron garnet interface is key, and the rare earth is key for the observation. So one more slide maybe on this topic is the domain. Domain wall motion, so domain wall speeds. So here I'm showing you the current density, the velocity versus current density. And there are several things that you can appreciate here. First is that domain walls, even though I'm injecting relatively modest currents, the domain wall velocities could reach 800 meters per second. It's pretty impressive. On top of that, we have a transition between a creep regime to flow regime that is on the order of 10 to the 10 amps per meter square. This is also very, very low. So basically, this material is extremely efficient for domain wall motion studies. So, we were at time we were a bit puzzled. So why do we get just a constant increase of the domain wall velocity? Because we know that in the ferromagnetic case, if the damping light torque becomes comparable to the DMI effective field, which is very small in our case, then the domain wall velocity should somehow saturate. But we don't see a saturation. We actually increase, the efficiency goes up. But then we have a model to explain that, and that is based on the exchange interaction between these two sublattices. So you have these two sublattices, you have a damping light torque. So if there was only one sublattice, then so this is a top view of this region of the device, and the current going is like this. So you had the damping light torque is try to kind of tilt these sublattices along one direction. However, since the exchange interaction, as I indicated before, is very strong in this material, then it acts like a restoring force. Therefore, it acts like a second torque on the domain wall. Therefore, we never reach within the limit of our current. We never reach the saturation, and this is confirmed by the model here. All right, so this is all about the domain wall motion studies that we have done. So in the last maybe 5 minutes or so, I will talk about this thermal spin drag and the non-local magnetization detection. So this is, okay, we are changing gears now. So we are going into a slightly different device schematics, but the materials are the same here basically. So we wanted to know, okay, now we can measure the out-of-plane component of the magnetization in a local geometry by using Hall effect. Why not doing in a non-local geometry? But there wasn't any effect that we know of that would give rise to a signal in a non-local geometry. Non-local geometry means that you are basically using some heater at a distance from your detector, and you expect to measure some signals in this detector. So, so what I expected is that in this device is that sending some AC current through this heater layer, I have an out of plane and in plane temperature gradient underneath, building up underneath platinum because of this thermal profile that you have. Okay. So, and we measured also two kinds of samples, one in plane sample and one out of plane sample, so that we can also distinguish between different effects. So now I'm focusing on the in plane samples here. So this is the measurement for different devices that are at different distance from the heater layer, and you see that there is some sinusoidal form of the data. Like the data shows some sinusoidal form. So it looks like a sine 2 phi behavior with some contribution from cosine phi, but the cosine phi was not so clear because it seems to be dominated by the sine 2 phi. So in order to confirm the cosine phi behavior, we did also the field sweep measurement. So field sweep means that magnetization rotates by 180 degrees, and that would basically separate. You will be able to separate the contribution from this cosine phi and sine phi. So okay, so we have cosine phi contribution for sure. We have a sine phi contribution for sure, but where do they come from? So the cosine phi is easy because it's we know that there is spin-Seebeck effect. So there is a temperature gradient out of plane, and that would be basically give rise to a inverse spin Hall effect in platinum that follows this cosine phi contribution. On top of that, now we know that we also have an in-plane gradient, and that in-plane gradient should give rise to a more recent discovery, let's say the spin-Nernst magnetoresistance. So it's like a spin-Hall magnetoresistance. However, the magnetoresistance, so the sine 2 phi behavior, it's it is driven by the spin-Nernst effect rather than the spin-Hall effect. And spin-Nernst effect is the thermal counterpart of the spin-Hall effect. So you need to have a temperature gradient to drive the spin current, and not a charge, not like a charge current. Okay. So I will maybe speed up a little bit so that I can come to my conclusions here. So these we understand. So these are already known. However, on top of these two well-established signals, we have seen another signal. So this is an in-plane Tully-Myron garnet, and this is with an out-of-plane field sweep. And there's a clear difference between when the magnetization is saturated in one direction or the other direction. Okay, and that becomes even like clearer when you measure an out-of-plane Tully-Myron garnet. You see that there's a significant, like not significant, but let's say appreciable signal here as a function of the heater current that also grows. Okay, so where does it come from? So we look at the, okay, so we now know that electrically driven signals, we have two contributions. We have this spin Hall magnetoresistance, so like this planar Hall effect-like signal, sine 2 phi behavior. We have also this anomalous Hall effect-like signal, which is much smaller, but still measurable. And now we want to compare this with the thermally driven signals in a device geometry that looks very similar. So in plane signals, okay, now I got rid of the spin Seebeck signal. So I just measure, just showing you this sine 2 phi behavior. That is the spin Nernst signal. So this is spin Hall signal. This is spin Nernst signal. And now I'm expecting I'm looking at this out of plane signal. And if you look at this comparison, so from this one, I expect this signal to be this much small. Therefore, there is some additional contributions that occurs due to well, in these thermally driven signals. So let me briefly explain that, and that would be my last slide. So our idea, our hypothesis is that we know that in these devices, there is an established outer plane temperature gradient, and there's also an in-plane gradient. So the outer plane gradient, basically what it does is that it, due to the spin-Seebeck effect, it pumps some spin current into the platinum with the spin current, spin polarization along this line. However, this is not a good geometry for inverse spin Hall effect. So this spin current cannot be converted into a charge current in our device geometry. So there must be an additional mechanism. So this additional mechanism is basically this in-plane temperature gradient, and this temperature gradient drags this additional spin accumulation in the platinum. And now with this additional electromotive force, we are able to detect a transverse signal that is proportional to the out-of-plane temperature gradient. And if you do some very very crude calculations, there must be that there is some free electron polarization in the platinum in these measurements for this set of parameters on the order of 0.12%, so which is reasonable. So if we found like 100%, I would be very skeptical. Or if we found like 10 to the minus 7, I would be also skeptical. But finding this number made me kind of reassured that this effect is feasible. All right, so to conclude, so I hope that I was able to show you that magnetic insulator is an excellent playground for spin transport and dynamics and magnetic manipulation, and in spintronics in general. And then we are able to observe, generate efficient spin-orbit torque switching in this tool in garnet platinum, similar to metallic samples, and also very efficient domain wall motion and interface-driven chiral magnetism occurring that is very open to basically a new, opens new avenues for further devices and research. And finally, I showed you a new magnetotransport phenomenon that occurs and that occurs in this non-local devices, and that is allows us to detect the out-of-plane component of magnetization in insulators. And before finishing, I would like to thank my former advisor at MIT, so Professor Jeff Beach, and my colleagues Lucas Carreda, Felix Büttner, and Mantao Huang, and our collaborators who provided the samples and stimulated stimulating discussions on these different experiments that we did all together, and my current advisor at ETH Zurich, Professor Pietro Gambardella, for also collaborating and offering me using of the labs. And finally, thank you for your attention.
Thank you, Zhang, for the very interesting talk. So if you have questions, please use the raise hand button in Zoom. And if you're on Twitch, please type your questions in the chat box. So the first question will be asked by Professor Brugel. Please go ahead and unmute and ask a question.
Hi, thank you very much for this very nice talk. I'm not working on these materials, therefore I have some simple questions. Yeah. You showed at the very beginning of your talk a wonderful TEM image where you show perfect growth between a rare earth garnet, iron garnet, and I think it was GGG, this gallium garnet. Yes. And I was wondering, I guess you grow it on 111 GGG, and as far as I know, you have two different growth possibilities. You have two different interfaces, if I remember. One is, so to say, the iron oxide gadolinium interface, and the other one is the thulium iron oxide gallium interface. And I was wondering whether the difference in the interfaces have an influence on the rare earth diem rare earth contribution of to the DMI?
Yeah. Yes, thank you for this. Yeah, very interesting question. I'm sure that there are some differences, but as an experimentalist, I think it will be very difficult, very challenging for us to be able to control this interface at this atomic level, as you would prefer from a theoretical point of view. Because in the end, my colleagues, I mean, they did like a follow-up study, so I was not involved in that, but I read the paper. So they have shown a clear link between the presence of the rare earth and the DMI occurring at this interface. Therefore, I would strongly, yeah, I mean, I think, I mean, I have strong belief that if you have a rare earth rich interface, that would potentially give rise to a large DMI. But that needs to be tested, of course. That's my experimental feeling. But, and unfortunately, we don't have that much good control of the interface at this desired level, let's say.
I have a second question, if the chairman allows.
Yes, please go ahead.
How large is actually your domain wall width?
So the domain walls are, I mean, we can only calculate because we cannot right now measure it. I mean, I actually, I don't have the data, but what we calculated, it should be in the order of between 10 and 20 nanometers. But that needs to be confirmed by measurements. It also depends very much on the thickness. So we this estimation was based on a thin film that is like 5 nanometers. So, but I know that if you make it very thick, you can also observe bubbles, and then the domain sizes also could get pretty large. But we know that it's not in the order of hundreds of nanometers, because we were able to observe magnetic bubbles in this material, though in a very thick form, like 25 nanometers, 30 nanometer form, we were able to observe magnetic bubbles, and these bubbles were on the order of 400 nanometers, 500 nanometers. So I expect that if there's like, I mean, the domain wall width should be in the order of tens of nanometers, if not smaller.
You had a very beginning, you had a wonderful picture of many rare earth garnets as function of temperature, the saturation magnetization, but the thulium one was not on it. I think.
Yeah, because this is, I took from this review paper, basically this thulium is not on it. Actually, all the materials that are, I mean, apart from gadolinium here, all the materials that we studied so far, they are not on it, but thulium has a compensation temperature which is theoretically 1.5 Kelvin, but there's a but, because there's all, I mean, you can never control the stoichiometry in a perfect way. So these are bulk, these graphs, they belong to their calculations for bulk materials. But in thin films, you always have deviations in the stoichiometry. So I have data which, I mean, we didn't publish, but I think I can tell you, because I already presented this in other conferences, that we have thulium iron garnet which shows compensation up at 40 Kelvin, 120 Kelvin. So the compensation temperature can be tuned very, like in a very in a wide range of temperatures, basically. So if you if you play with the composition.
If you cannot control 100% the composition, and the composition is responsible for the compensation temperature, isn't that a danger for technology?
No, because these materials were basically, it depends on how you grow your material. So if you start from a stoichiometric target, and if you do a sputtering deposition, I expect that the compensation temperature doesn't move so much. But if you want to study the compensation temp, like let's say if it's for you better to have a compensation temperature that is, I mean, close to room temperature for the type of measurements that you want to do, then you can engineer that. But let's say, I mean, I believe that with enough, like with like reasonable engineering efforts, this can be very precisely controlled.
So when you say you can control the compensation temperature, what do you need to control actually in the composition?
You need to control the stoichiometry, and but something that you cannot control is the site occupancy of this rare, like, or these ions, because basically this is this idealized picture, right? So you have all the dodecahedral sites are occupied by rare earth, tetrahedral sites and octahedral sites are occupied by iron. So if this happens, normally you should have perfect stoichiometry. But if you observe that the compensation temperature deviates from the theoretical prediction, it means that these ions are not where I'm describing it here. So there could be two things. So if you either so there are excess of some rare earth or some less the rare earth than what you need, or that they occupy different sites. So that could be also another way. But the control of it is not, for now, is not, let's say, possible. I know that I can make it perfectly stoichiometric, for example, if I use another deposition method or if I control it more precisely. But let's say, I mean, I have a feeling that you can also engineer. I mean, it's just a lot of work. I mean.
Thank you very much.
All right, so we have another question from David. He asks, you mentioned magnet insulators has a lot of advantages, but is there any disadvantages of magnet insulated materials compared to metallic ones?
Yes, there is definitely one disadvantage I know of, is that because they need to grow epitaxially. So you need some epitaxial growth on top of some like a GGG. I know that there are some efforts to grow this material on silicon dioxide. Indeed, this when I gave this example, these three garnets were grown on GGG, but the last one is actually grown on silicon dioxide. So, but the properties of it is, let's say, from a Spintronics perspective, is poorer with respect to the other one. But let's say, okay, to wrap up, so the disadvantage of the garnet films is that you need to start growing the garnet films and then build your device on top. So that's basically, you have less flexibility on where you can use your garnet films, and they need to be grown on a specific substrate, and they need to be epitaxially grown. And there is also a high temperature involved in the growth, because otherwise you don't get this nice quality if you don't anneal your sample, or if you don't keep the temperature of your substrate at a high temperature during the growth. So these are the like apparent disadvantages for me, but these are all like from a materials perspective. So from Spintronics perspective, once you have the material, and if you know that you can, let's say, if you can design your device and you can allow your magnetic layer as a first layer in your substrate, then there is no disadvantage for Spintronics, in my opinion.
Thank you. I suppose the electric readout is also still going to be challenging for device level application.
Yes. Okay. Yeah. Not to mention, of course. Yes.
Do you have any other question? I want to ask one question about the last part of our talk about the thermal spin drag. If I understand the mechanism you described correctly, it's a two-step process. First, you have perpendicular temperature gradient pumps the spin into platinum, and then you have in-plane temperature gradient drags move the spin, which gives rise to the let's say the inverse spin Hall effect, something like that. But if this is the case, shouldn't the signal be 4 omega instead of 2 omega? Shouldn't it be, the frequency should be 4 times of the driving frequency, because it's
I think
you're square.
Yes, you're right, but there's also a but, because then the picture that I'm drawing here is like a naive picture, basically. So it's like still I'm sending an AC current, and I expect the thermal signals to appear in the second, fourth, and the higher harmonics. So I mean, to be honest, we didn't check the fourth harmonic. But it's likely that I get some of the signals in the fourth harmonic as well. But you're right. I mean, in this naive picture, it looks like we should get kind of a fourth harmonic signal. However, I think the real mechanism, or not the real mechanism, but if you like, the microscopic mechanism is not like as simple as I describe here. So I still, I was able to measure it in the second harmonic, and that seemed to be the only explanation, a reasonable explanation to me. That also kind of made sense when I did some rough calculations, basically.
Thank you. Is there any other question from the audience? Okay, so if there's no other question, I want to thank the speaker again for the very interesting talk, and I want to thank everyone for participating.